Okay, so welcome to the final part of this. So this is Unit 9. This is for A-level. This is for separate science physics only. And this is where we look at nuclear decay and nuclear energy. So this is basically fission versus fusion, how we can use it. So if you're doing double award, you don't need to watch this. Stop now. Go back to the other videos unless you're interested. If you're doing separate, this is for you. Okay, so what we're going to look at. So we're going to look basically at fission and fusion. We're going to look at them in depth, different parts of it, some of the pros and cons as listed here. Videos, lots on fission, lots on fusion, from Doodle Science, Fuse School, Cognito, Science Shorts, and of course Seneca Learning there again. Okay, on to the first process then, nuclear fission. Alright, so nuclear fission is basically the process of splitting heavier nuclei into smaller nuclei. Now, most fissions that undergo in a nuclear power station are not spontaneous. They don't happen by themselves. We have to induce them. We have to cause them to happen. To do this, we do it with slow-moving, or sometimes called thermal neutrons. Basically, we fire a neutron at a nucleus, it's absorbed, that destabilizes the nucleus, and then it splits. As it splits, it releases more neutrons. These neutrons, as you can see here in the diagram, can go on to produce further fissions. And this is why it's called a chain reaction. The product of one part of the reaction can create more. Now, you can see here, just within these three, we've got 1, going to 3, going to 9. Very quickly, the rate of this reaction would speed up faster and faster and faster if we don't control the number of neutrons. And this is where you get a chain reaction, a meltdown, nuclear explosions, if we don't control the number of these neutrons. So to do that in a reactor, we have a few different things. One, we make the walls of a reactor out of thick concrete. This contains the pressure, but it also contains the gamma radiation being given off by this reactor. They also contain a moderator. So the moderator, made in this case out of water, can be made out of graphite. This slows the neutrons down so that they're more likely to be absorbed. If they're going too fast, then they'll just bounce off, they don't get absorbed. This is done by friction, so this creates heat energy that can be used in our power stations. Now, the other thing our reactors contain is fuel rods. Not fuel rods, sorry, control rods. Control rods made of boron. These can be raised or lowered to control the rate of fissions. Basically, these control rods are there to absorb excess neutrons. So what they try and do is basically get it so that each reaction only produces one neutron. So the overall number of neutrons doesn't change. And we do this by raising and lower them. Generally, they're designed to fail, that they'll drop straight in, and when they drop straight in, they will absorb all the neutrons, hopefully, and stop a reaction from going on. Now, if we're evaluating fission, okay, some of the problems with fission. One, we can't control what's being made. Okay, so many of the daughter nuclei, the products of fission, have really long half-lives and are radioactive. The problem with this is it means that they stay radioactive for a really long time. Okay, now, fission reactors, on a good side, have a lot of safety features, which means they are very, very safe. If you look at the deaths caused by fission reactors, they are way lower than a lot of other forms of electricity. Plus, they don't produce any CO2 when they're actually generating, which is obviously a very good idea. Downside again, we have got to store this waste, and we're working on ways for this, and plans being placed to store radioactive waste for a long time very securely. Now, nuclear fusion. Fusion is going to be sticking together like nuclei. So here we have two not like nuclei that are fusing together and releasing energy. This process is what's going on in stars, as we learned earlier. So here we've got two hydrogens in the form of deuterium, both the deuteriums forming in to make a helium. Now, fusion reactors. These are currently just in their experimental phase, and none have actually been producing energy yet. Close, but not yet. But basically what you have, to get a fusion, you need a high temperature, high pressure, because you're trying to force together things that have both the same charge. So you've got to overcome that repulsion. So you need high temperature, high pressure to do this. Now, reactors designed to overcome these high temperatures and high pressures. Where we do this is strong metallic shells to hold the pressure, really powerful magnets to stop the charges from touching the walls so they don't cool down. And basically the problem with these high temperatures and high pressures makes these things really expensive and difficult to run. But we're getting there. Slowly but surely we are getting there. Now, if we're evaluating fusion, beauty of fusion is the products are really well controlled. Okay, for most of the fusion reactions that we're looking at to make power from is going to be producing helium-4. The energy released per gram of fuel is actually higher than fission because the fuel's really light, basically. And again, doesn't release CO2, only product is helium-4. It's clean energy if we can crack this. Problem is we need that high temperature and pressure to overcome the repulsions, which currently basically means that anything that's out there at the minute is energy negative, which means we're putting more energy in getting this stuff up to the high temperature, high pressure than we're actually getting out. So you need to be able to do a direct comparison of these two. So a table like this is very useful. So you can see that fission is our heavy nuclei being split into lighter ones. Generally the fuel we use is uranium-235. There's an example reaction. And if you take note, the numbers across the top and the numbers across the bottom are the same as you go on. You got things about the reactor designs and issues as we spoke about. Fusion, stuff's there, you can read it. Example reaction, as we've got. Like I said, main problem at the minute is maintaining that heat and that pressure. So I'll just leave that there for another 10 seconds for people to have a read through. Okay, so over to you. So this is the last set of questions. Okay, and what you need to do then, obviously if you're on YouTube, the link for these in the description. If I'm watching this via PowerPoint, stop the presentation, click the document, it should open up. If you're got it open in the app, don't open it up in browser. If you're on a computer, open it up in the app, and there we can go. On the next slide, we'll have the answers on it.
Okay, so final bit of this. So this is where we are looking at now the nuclear energy fission and fusion part of the course. This is the last bit. This is for separates only. So we're starting with 2018 foundation paper. And this is question 2. So complete the diagram. So it's got a half-life of 5 hours, so every 5 hours is going to half. So dead easy to nice and start us off. 800 halved is 400, and 400 halved is 200. Okay, so we've got a nuclear reactor here, plenty of stuff to read, should read it all. And we've got an equation, how many neutrons are released? So that's there, so that's 2. Then we need to underline it, complete the following sentences about the nuclear reactor by underlining it. The nucleus uranium is made to split when it captures 1 neutron, just 1 there. For fission to occur, the neutron must be slow moving. If it's too fast, it will bounce off, and that's done by the moderator. And we prevent uncontrolled chain reactions by control rods. Why is it difficult to store the waste from a nuclear power station? So you've got to basically, you've got to it must prevent leaks. Yeah, we can't have any leaks. And the other problem is for a very long time, due to long half-lives. Some of these things have like thousands of years half-lives, and that's the problem. Okay, on to page 3. Nuclear fission and fusion. Higher 2018, whoops. Fission and fusion are both used to produce heat energy, or both produce energy. Describe and compare controlled fission and fusion reactions. So, if we start off talking about fission, okay, so we have heavy nuclei, capture slow electrons, neutrons, sorry, because we just wrote that down. Capture slow neutrons, and split into smaller nuclei releasing energy and neutrons. Okay, now we've said about controlled, so we can control using control rods, and they're normally made of boron, so boron control rods to absorb excess neutrons, and we use a moderator to slow the neutrons down. Okay, when we're talking about fusion, okay, so we have light nuclei fusing to form heavier ones, and energy. Okay, and for this to happen, we've got to have high pressure and temperature. Okay, now if we're comparing them, the important things in the comparing, well, we've done one's about splitting, one's about joining. We don't need to write that down again. Okay. Important things when we're comparing: fusion releases more energy per kilogram of fuel. What else can we put in here? Fission creates radioactive waste. Fusion doesn't. What else should we include in here? I've run out of room, so I'll just talk through the rest of it. Probably you want to talk about in here that fission reactions can overheat and cause meltdowns if they're badly controlled, whereas fusion is much safer. You don't get an uncontrolled chain reaction in a fusion reaction, and they're the main points on that. Okay, a typical fusion reaction is between tritium and deuterium, and we produce that amount of energy. Calculate the number of fusion reactions needed each second to provide an energy output of 6.2 megajoules. So all we're going to do here is do 6.2 times 10 to the 6 divided by 2.82 times 10 to the minus 12, which is 2.2 times 10 to the 18 reactions. Okay, question where we are, separates higher 2019. Right, question 6. Explain how the reactor is designed so that fission is sustained and controlled. So these are all the things we've just written so far. So moderator slows neutrons down. So they can be absorbed. And we have control rods that absorb extra neutrons or neutrons. So only one can cause further fissions. Basically, the two marks are for the lines there. One saying about what the moderator does and why we do it. One for the control rods and why we do that. Right, so we've got to complete this equation here. So if we add at this top number, you can see that we're 2 short. So we've got to have something with a 2 at the top. And it's going to be neutrons, because if you look at this bottom number, those two add up. So the bottom number's got to be 0, so it's 2 neutrons. 1 marked for the 2, 1 saying it's a neutron. Explain why a nucleus of uranium-235 undergoes fission when it absorbs a neutron. Okay, becomes unstable. Why is it unstable? Due to imbalance of protons and neutrons. Okay, one product of fission of uranium is strontium-94. Strontium-94 undergoes beta decay with a half-life of 75 seconds into an isotope of yttrium. Yttrium also undergoes beta decay, half-life of 19 minutes, produces a stable isotope of zirconium. Write a balanced nuclear equation for the decay of strontium-94 into yttrium. So strontium-94, and we've got the strontium number up there, so we just copy it from there, goes to yttrium, it's capital Y, 39, still 94, plus our beta particle. State what is meant by strontium-94 as a half-life of 75 seconds, so that means that half, or let's rephrase that slightly better, in 75 seconds, half of the strontium-94 nuclei will decay. Explain whether long-term safety precautions are required for the disposal of the waste product of strontium-94. Well, no, because the half-lives of the strontium and the yttrium are short, and are short, so will decay to stable zirconium quickly. 2 marks, basically one for saying that the half-lives are short and one for saying what does that mean? Well, it means we're going to make stable zirconium pretty quickly. Okay, so that brings us to the end of all of these exam reviews. Hopefully it was helpful. If you want, mark schemes are all available online for these questions. Just look for the question detailed above. If anything's not clear from what I've been through, hopefully they've helped. And thanks for watching.
Okay, so well done for making it to the end. Thanks for watching it. I know some of these are pretty long. And like I said, if they help, leave us a comment. If they don't help, leave a comment. If you'd rather the review bits, which make them really long, I'll put in separate videos. Again, let me know. It's not a difficult job to do, and I can put them in separate videos rather than putting them in the main video, and it will make basically 2 shorter videos. Please like, please subscribe, and hopefully they help with your qualifications.